our session can start when you're ready, Ezekiel.
Okay, thank you. All right, so we can start now.
Okay, thank you so much. Just hello everyone, I'm Kris Sankaran. It's nice to meet you all. I was thinking earlier, like I wish I were able to teach in person. I think some of the things that are the most valuable you get out of these sort of bootcamp experiences is when you meet all your other peers, or when you meet the students, kind of even just like informally, you learn a lot from one another, right? We can't do that this year, but then I do hope that you are a little bit more liberal with just reaching out, right? So we can't have informal conversation at just lunch or anything, but you can always email me, right? And feel free to reach out. Okay, so this session is on statistics and machine learning. I'm going to share my screen now. So my slides are here. Let's see if I can make it full screen. Oh, okay, this is fine. Okay, so I'm going to be talking about statistics and machine learning. 2 hours is quite a long time to just be listening to someone. So I prepared a list of questions. Actually, I'm about to copy it into the chat. I prepared a list of questions. I've also copied a GitHub repository, and I have a Jamboard open in case people have questions. Google Doc. I will put some of these links back when I start asking questions. So the Google Doc has a bunch of just questions I'm going to be asking you throughout the talk, because it gets sort of technical, right? This is, there's math and statistics. And if we need to discuss things, just reach out. Here's a GitHub repository. You know how they say in GitHub, you're not supposed to put all the data and the pictures and everything like that? Well, I had to just put all the data. So if you want to just rerun everything that I'm going to show you, it's all here. There's also some Colab notebooks that are down here that I'll be referring to. Okay. And the last thing, since it's kind of a long time for a session, probably about every half an hour, I'll just have really short, like 30-second stand up and stretch kind of breaks, because sitting down for that long will be hard. Okay, so with all that out of the way, let's get into Stat for ML. Okay, and I'll keep an eye out on the chat. So this talk has two main parts. Like statistics and machine learning is a huge topic, right? There's so many areas of connection. There's so many things that I could be talking about. And I do link to a few kind of philosophical overviews at the In this talk, I wanted to, instead of giving a kind of big overview, I wanted to dive very deeply into two topics. And I want you to feel like after the end of this lecture, you really understand the in and out of these two areas. One is understanding variational autoencoders. I'm sure most of you have at least heard of this. And then the other is about representation analysis. And the reason I chose these two topics are because they're showing how the two fields can influence each other in different ways. So the variational autoencoder I think of as a way that the flexibility of machine learning has helped advance Bayesian statistics. And then representation analysis is a way that I think of how kind of classical multivariate statistics is informative for understanding machine learning models. So we'll see the interplay going in either direction. Okay. How I like to learn, right? Whenever I learn anything, actually, not just in this kind of topic, I always try to learn things hands-on. I think there's much more to understand by tinkering something simple that you can really just get a feel for in your own laptop or like on paper with your own examples. I find when I try something like that, I can learn it much better than if I'm just reading some paper that's doing something that I'll never be able to implement, or it would take me forever to implement. And I can't get that same kind of hands-on feeling for it. I think, the whole point of publishing is actually just to be able to share your personal experience of some object or some new mathematical thing with other people. Okay, and I already linked to the GitHub repository. Okay, so now statistics and machine learning, right? What is the difference? Why do we even have a topic on this? So they have a lot in common, right? They both think about how do you study and learn from data. But that said, the way that they go about that question can be pretty different, right? And I think a lot of it comes from the difference in just the histories and the culture. It's not so much about the actual topic than the community of people who end up working on these topics, right? Kind of originated mostly in mathematics. And so there are a lot of people who are working in probability, versus in machine learning, a lot of it started in engineering. So people who are building real world systems. Statistics has a lot of connections to philosophy, right? So kind of the whole ideas of falsification or inductive inference, these are ideas that are discussed in pure philosophy circles. And then a lot of statistics is just trying to abstract away or mathematize that philosophy. Machine learning has a lot of connections in neuroscience. So there's a lot of analogies between computer systems that are learning and human systems or animal systems. And then statistics, it's often the final emphasis is on the kind of scientific thing that you've learned at the end. So there's always like this person in mind and you hope that they gain some insight. Versus in machine learning, there's often not even a person involved. There's some sort of automated system that exists in the world. Just think about kind of like a self-driving car, very canonical example. Okay, so here's the kind of, when I'm thinking of the analogies, this is what I have in mind. So the thing on the top, this is an example of a microarray trip. So microarray, this is some of the very first genomics studies. I don't know if other people are having trouble hearing me, let me know. But yeah, otherwise maybe just try turn on and off. I'm not sure. So yeah, this is a genomics kind of example. And then this is like an automatic port robot. So it carries containers on and off the boats, or this is trains. Right? So this is powered, it has AI to do all the kind of movement and lifting. This is a kind of data set that's used in a lot of modern statistics. Okay, so that's just some of the difference when you hear statistics, when you hear machine learning, what are the kind of associations that should come to mind? Okay, so let's get into some technical material now. So I'm going to be talking about variational autoencoders. My way of getting there, I'm going to be starting by talking about Bayes' rule. Okay, so, and we're going to start with a kind of very standard example for Bayes' rule before getting to the autoencoder. Okay, so what are some of the goals of modern machine learning or statistics, right? Often you care about inference and prediction, right? So you want systems that can both sense things in the world and help guide decision making, right? So there's all this information coming in, you want to be able to sense the things that are relevant, and then you want to use that in order to act. And they're often kind of three desiderata, right? First, you want everything to be fast. You don't want to have to run your model, start it, and then wait for 2 weeks before you can get realistic. So what I mean is, rather than just saying, I predict that the temperature tomorrow is going to be, 25 degrees. You say, I predict it's going to be 25 degrees plus or minus as much. Or you can even put a whole distribution over the predictions. And so you like, it's often better to have these kind of probabilistic estimates. And finally, you want it to be automatic, right? The more that you have to kind of tinker with everything just to get it to follows. So these are the three things that you often want in kind of machine learning and the intersection between statistics and machine learning. And I think variational autoencoders are a nice example of something which kind of has all of these properties. Okay. So Bayes rule. This is one of the kind of fundamental theorems in probability. Theta is some parameter. It's something that you're trying to learn, kind of the average temperature in the place that you're living, right? Kind of across all the days. X is something that you've observed. Right? So it could be the temperature that you've seen over the last 3 days. And maybe you're trying to estimate, you're trying to extrapolate something in general based on something that you've seen a little bit. Right? The formula is, you know, I can read it out. It's not that illuminating to just read it out. To see the proof, you just cross multiply. Right? If you multiply this times this, it ends up being the joint distribution for theta and x. And if you just multiply these two together, it's also the joint distribution between theta and x. So that's why this equality holds. But how do you actually interpret it? The interpretation is something like this. The interpretation is you have some initial belief about the world. That's P of theta. Then you observe some new information. So this is the P of x given theta. So x is some information about the world. And then once you have that new information about the world, you update your belief about the world. So think of P of theta as your initial belief of the world. X given theta is new information that arrives. And theta given x is your updated belief about the world. So in a way, Bayesian statistics just kind of summarizes the whole process of learning. New information arrives, you've learned something. I often use this kind of notation to refer to kind of the density proportional to. So the reason this is true is because only the numerator depends on the normalizing constant. It's not actually influencing the shape of the curve. And that's why you can just throw away the denominator and just write the proportion. Okay, this is a little bit abstract. So I think it will be useful to look at a specific example. So here, this is the kind of coin flipping with the beta binomial distribution example. So imagine your task is this. You are given a coin. You don't know whether it's a fair coin. It could be, you know, coming up heads 10% of the time. It could be coming up 90% of the time. Your goal is to figure out whether this is some sort of loaded coin, right? How would you approach this problem? One way to think about it is to use Bayesian statistics. You can start with some initial belief about the distribution of coin flips. So here I'm saying its theta is distributed according to some beta distribution.
Oh, sorry, please continue.
Oh yeah, don't worry. Okay. Yeah, so here I'm saying theta is from some sort of beta distribution. And then the likelihood is going to be some binomial. So here's what the prior would look like here. So I'm imagining it's, you know, you're not really sure between 0 and 1. It could be totally always coming up tails. It could always be coming up heads. Or, you know, probably more likely, but not that much more likely necessarily, it would be kind of a fair coin. All right, and this is what that prior might look like. Okay, so now this is exact 10 flips of that coin. And it looks like I've gotten 4 heads or 4 gold coins, and then the rest of them are tails. And now you need to estimate kind of what is the distribution, like what do you actually think? Is this a fair coin or not? Right, that is the question. Okay, so we are at the very first Google Doc question. So the question is, if P is the probability of the coin coming up gold, then in what direction do you expect the posterior to move after having seen the data, right? So remember, the prior has this shape. You're kind of not sure whether it's between 0 or 1. You think it's probably around the middle. Outcomes. You should update your prior to be some sort of posterior. The question for you all is, how do you expect, should it be moving to the left? Should it be moving to the right? Should it be getting more concentrated? Should it be getting wider? To speak, because there are a bunch of you on camera, just go ahead and write your answers here. I'll give a minute to think about it. So again, here's a prior. This is the data that you observe. Want to try? It's okay to be, just make a guess if you're not sure. It's all anonymous. I got no idea who's editing right now. Okay, so we have one vote for left-hand side. You want to explain why? Give it another 20 seconds. Okay, so whoever, the brave soul who wrote it, okay, there's a question. Yes, that's it. That is exactly the explanation. Yeah, so what happened is you observed only 4 out of the 10. So this gives you, this starts suggesting that it's less than 50-50, right? Not that much evidence, but it's some evidence that it's less than 50-50. The more data that you collect, the more you would be sure, right? So that's exactly the picture here. So it's moved a little bit to the left-hand side. Okay. There's a little bit of history. I think this is kind of a fun things to know whenever you study these topics. So this problem was originally studied in 1814. It started in the problem that's called the Laplace's sunrise problem. So he asked, what is the probability that the sun will rise tomorrow? Given all the sunrises that you've seen in the past, right? You have some prior on what you think the probability of the sun rising tomorrow is. And then you observe all these days in which it has to come up. So what is the probability that it comes up tomorrow, right? So that is the question, and that's why he developed this whole theory. So you can see how he actually solved it. It's kind of fun. But okay, so why did it move in the way that it did? The reason is when you write, so there's like the intuitive explanation that we just gave. That's, you become a little bit more sure that it's less than 50-50 because you have fewer, you see fewer gold. If you want to be more precise, what you do is you write down the beta density and then you multiply it by the likelihood. And this ends up being proportional to this quantity. And the point is, it's still a beta distribution, right? So sorry. So this is still the prior. I'm going to show all the steps that go for the likelihood and the posterior, and then it's still a beta. But formally, this is the shape of the red curve, right? So the red curve, the prior, has this parameterizes a whole bunch of distributions that are between 0 and 1. And since they're between 0 and 1, they're a good distribution put on probabilities, right? If they weren't restricted to be between 0 and 1, you could imagine putting any kind of probability distribution. But since it has to be between 0 and 1, you want to make sure to do something like this. So now we're at the second question. Huh. The question?
Going to different places today.
Okay, oh, sorry about that. Okay, but we're at the second question. The second question is this. I have this kind of formula for the red curve, for the prior densities. It depends on A0 and B0. How does the shape change as I vary A0 and B0? That's the question. If you want a hint, you can go to this link. So I'll show you a little bit what it looks like in case you don't have internet. Okay, so this is the original thing. Here's alpha, here's beta. Here I'm changing alpha. Here I'm changing beta, so that's like B0. Something kind of funny happens if I make them really small. So if I make it really small, oh, it just disappeared actually. So this implementation is bad. But here, you can see things. So anyone want to summarize what's going on here as I change these? So here, they're calling it X, but I'm calling it theta, but it's the exact same formula. Anyone want to summarize what is happening as I vary these parameters? You just summarize it here. Yep, we're all just waiting for answers here. Okay, I think a lot of people got this. Maybe give it another 20 seconds. Oh, yeah. Okay, there are a lot of good answers here. Okay, we're gonna move on. But I think I can tell that a lot of people also are writing things. If you want to continue writing your answer, I encourage you you can go ahead. You're not gonna miss much because it seems like you're getting this. And kind of just to summarize the different answers that are coming in, right? Pretty much everyone is correct here, right? So as you move, like A0, here it's alpha and beta, but then here it's like the relative ratio between alpha and beta is telling you how close you want things to be between 0 and 1. So when alpha is much bigger than beta, then it's like you're pretty sure it's close to 1, but you don't think it's close to 0. Vice versa, if I make my beta much bigger than alpha, then it's like I'm pretty sure that it's closer to 0 than it is to 1. And when they're about equal, then then it's kind of near 0.5. And also notice there's something no one mentioned. When they're both really big, then it's a pretty narrow. You're pretty sure about where you think things are. When it's relatively low for both, then it's a little bit wider, right? So here you're less sure of where it is. Okay, so that was kind of what I wanted you to take away from this density. So it's just this. Now you have some intuition for what this formula means. Okay, so that is the prior density. Here's the likelihood. So binomial distribution, this is a formula for it. Probability of coming up heads. This is the probability that you see X heads in N flips. So each one had a probability theta of coming up heads and 1 minus theta of coming up tails, and their N choose X ways of reordering everything. So there's another demo. You can, I don't know if I follow this copy, I'll copy this link and share it in the chat. If you want to do the same kind of playing around with the densities for this distribution, you can also do it in that link. So this just gives you some intuition. But I'm going to skip ahead to the posterior. Actually, is that one of my questions? Oh yeah, no, let's go ahead. Let's ask number 3. If theta were 0.1, how would the figure change? What about 0.9? And then to answer this, I'll go ahead. It's 0.1. And this is not a trick question. You have a certain probability of coming up heads on the tail, or sorry, probably coming up heads on the coin. And then the question is, as the probability of coming up heads changes from 0.1 to 0.9, what is happening to this distribution? If you want extra question, how does it change as you have different numbers of coin flips? So here's 100 coin flips. Here's you only have 2 coin flips. Okay. For which? The binomial? Okay, I think people got this. So answers are close, or actually, yeah, pretty much everyone got it. The answer about what happens when the number of trials change is still not there. So, okay, people will correct when you have some fixed number of trials. It peaks around where that P is. So like, I'll do the 100 again. So when you have probability of 85% of coming up heads, the peak is right around 85 coins coming up heads, but there's pretty good chance that it will come up to, 80, 82, 81, 82, 83, maybe like 89 wouldn't be that surprising. If you see only 60, that would be really weird, right? So that's what happens when you change P. So it changes where the thing is centered, and yeah, it just changes where the thing is centered. As you change N, what happens is the breadth does change, but in the opposite direction. So when it's very few, then it kind of, it's not as concentrated, right? There are fewer things to evaluate it over. So here, okay, let's make it 20. So when it's 20 and say 10% chance of coming up heads, then the highest is at 2. You wouldn't be too surprised if you see 1 coin flip or 3, or 1 heads or 3 heads. It would be really strange if you saw 18 or 19 heads. Versus when I make it really large number of trials, then it kind of, there's a whole swath of the area that just has 0 probability essentially. And then it gets pretty concentrated around its expected value. Okay, so now we know everything about Bayes' rule for beta binomial. Okay, so now you can use Bayes' rule. So I'm just multiplying the 2 terms together. This was the likelihood, it's some binomial. Here is the prior, it's some beta. I ignore this term because it doesn't have anything to do with theta, right? So I'm only paying attention to the terms that have to do with theta. And then I collect the like terms. So the theta, it's a0 plus x minus 1. The 1 minus theta, it's this b plus n minus x minus 1. Okay, actually this shouldn't have a 1, I don't think. It should just be b0 plus n minus x. I forgot a 1 here. Okay, but the main idea is that it's still a beta distribution. And what it means is that if you saw a lot of heads, then it starts moving your alpha parameter, or the A0 parameter, it increases that a lot. If you saw a lot of tails, then it increases your B0 parameter. So what essentially happens is, if I have a whole bunch of tails come up, then it's like the density gets concentrated around there being a lot of tails. If I had a lot of heads come up instead, then your guess about the probability of the coin increases closer to 1. So that's the mechanics of Bayes' rule. So you start off not being sure, and then as you see lots and lots of heads, it updates the parameters so that it increases that one parameter a lot and the other one by not much. And then it concentrates around the new correct value. Okay, and here's a little simulation, just illustrating this idea some more. So here I have the green coin and I have the gold coin, or the orange coin here. And here it seems like as I flip more and more coins, I'm observing a lot more times that this green coin comes up. I don't see as much happening for the orange coin. So now kind of the point is, how do you update your distribution, right? So you start off with some beta distribution. How does it reconcentrate around a new probability given this observation? And what I show you here, this is actually how it changes. Right, so this is at the point it's already concentrated. So here it's learning, and it's starting to notice that there are a lot more green than gold. So it's starting to center more and more around this low value, and then it gets more peaked. And I just have this running on a loop. Right? So as this thing increases, it gets more and more peaked. Okay, so now this is kind of everything about Bayes' rule. This is an example of a conjugate model. Why is it called a conjugate model? It's because the prior and the posterior come from the same family of distributions. They're both beta distributions. And the kind of neat thing we were able to do is we were able to write down just the formula. And just from the math, just from writing down the formulas, we're able to figure out the posterior distribution. This is not something that you can do for most models. This is like a very special case for certain models. So what we're going to need to do, we're going to need to substitute all this kind of analytical calculation for a little bit more automatic computation. Okay, so let me see if this is a good place. Okay, so we'll have one extra piece, and then we're gonna take a short, like 1 minute break. The final idea I want before break is to think about, there's something called like the variational idea. So when you hear variational autoencoder, what does variational refer to? What variational refers to in this context, it means you transform a mathematical problem. So the mathematical problem is kind of calculating all these densities and applying Bayes' rule using formulas. And you turn it into an optimization one. So what does that mean, right? The idea is you think about this kind of whole space of probabilities, right? So imagine each point in this picture is a different probability distribution, right? Maybe the different points can correspond to different beta distributions, right? So when it's a very high concentration around 0.9, that could be one of these points, it could be like right here. And when it's concentrated around 0.1, it could be out here, right? So each point in this space is a different probability distribution. The idea is that when you've observed some data, there is a true posterior distribution that is P, Z given X. That might lie at this kind of blue point. Now, the goal is to define some sort of optimization, some sort of set of candidates. So maybe your candidates are this region Q. And you want to find the candidate distribution that is as close as possible to this posterior. Posterior, if it had been a big gray blob that contains the blue point, then Q and P would overlap. Right? The optimal thing to choose among the Qs would be to just put it at where the true posterior is. But what I'm showing you is the more common case where the distribution, the one that you really care about, is a little bit outside of the set of distributions that you're allowed to consider. The reason you're only allowed to consider a smaller set of distributions is because these are the ones that are computationally very tractable. So these are the ones you can calculate very fast. They don't include the true one, but maybe you can find one that's kind of a minimal distance to the true one. So that's going to be what variational inference is going to be about. Before diving in to a variational autoencoder, let's take like a 1 minute, just stand up and stretch. Yeah, so get some energy. If you had been falling asleep during the beta binomial, now is your chance to wake up. That's right. Okay, so that's 1 minute. Let's get into variational autoencoders. Okay, so this is the model. We're gonna first present it through some pictures, and then I'm gonna show you some code. So what is just for some vocabulary, right? Before we look at anything very specific. So imagine you have a whole data set. You have a whole bunch of samples I, so x1 through xn. Now for each of these xi, there exists some zi, which summarizes its essential character, right? So this is some sort of, you observe the full xi, but maybe there's like a very succinct description, like a representation of that xi that very concisely summarizes the entire xi. So maybe you imagine z as being like 2 or 3 numbers, but x might be 100 numbers, right? And you have this kind of xz pair for every single element in your data set. We're going to be talking about decoding and encoding. So what decoding means you start from that succinct representation and you extract some full observed data point. And encoding means you start with the observed data point and then you turn it into its succinct representation. So in the usual kind of MNIST example, what this means is you observe a whole bunch of digits. You have 9, you have 8, you would have a whole bunch of other digits. And then you encode it into some low dimensional space. So encoding takes the digit and it turns it into this latent code. So here you have a zi is 2-dimensional. So it's your position in this space. And I've actually drawn it as a little distribution rather than just a single point, because really what you would like to do is you'd like to have some sort of more probabilistic encoding. So I want to encode it and say, I'm pretty sure it's near here in the Z space, but I wouldn't be too surprised if it were a little bit off from there. And then decoding is a process of starting from the Z's, starting from this kind of latent representation space, and then creating an image. So going from the representation to an observation. Okay, so here's a real world kind of more complicated example. So this scatter plot, this is a latent representation. So it's only 2 dimensions, or it's like a projection of, I think, like 60 dimensions. And each point corresponds to one of these digits. And the idea is that as you're kind of in certain areas of the latent space, all the digits out here, all of these are all 3s. All the digits out here, these are all 7s and 9s. And it kind of makes sense that 7 and 9 go close together. They look pretty similar to one another. Okay, and the point here is that you can observe all the classes in the original pixel space, but once you reduce it to the representation space, which is much lower dimensional, right? MNIST digits are, vector. But then if you look at the representation, you can reduce it to just a smaller code and it summarizes essentially the same information. And what's going on in this side of the picture is this is decoding in action. So I've taken, or I didn't take, this is from some paper. You take a single point, and then given that point, you can generate many examples of what are some images that correspond to that representation. And the idea is that kind of all the different rows, so if you pick a 0 from this latent code, then it generates not just a whole bunch of zeros, but they all look pretty similar, right? So maybe this one's a little bit more slanty than the others. Maybe this one's a little bit bigger, but then you generate a bunch of similar zeros. Versus if you choose another area in 0 space, you get a different type of 0. But there's some variation. Representation. We're going to need hierarchy. We're going to get it by computation using variational. Okay. So if you'd never observed any MNIST digits, then you would start with a prior over all these kind of latent codes. And since it's kind of prior, and then you observe a likelihood. So given a particular Laplacian code, you have a likelihood over images. We're going to parameterize that likelihood by theta. But it is binomial. Here, what I'm going to do, I'm going to say the prior is going to be a normal distribution, so a d-dimensional normal distribution. And then the likelihood, this is also going to be a normal distribution, but the key difference is my normal distribution is going to have mean mu theta, so the mean depends on where you are in the z. This is a multivariate normal distribution. Both of these are multivariate normal distributions, right? Actually, I should have written different. These are usually different dimensions. So think of this as being like a 60-dimensional normal distribution, and this as being a 500-dimensional normal distribution. So you have 500 different means. And what this notation means is you have a diagonal covariance matrix. So it means you have sigma squareds all along, variances along the diagonal. And the question is, so next question on the Google Doc. Given Zi, given that you observe some latent code, what is the correlation between neighboring pixels in the image space? So, you can imagine having two pixels right next to one another. What is their correlation? And if you can answer that, a follow-up question is, why might neighboring pixels in Xi have similar values most of the time? Okay, so this is a trickier question, but I want you to give it a shot. This is number 4. Right here. If you'd like some clarification about the question, we can go to the Jamboard and we can try some calculations. For reference, this is the distribution of X given Okay, we have some ideas. Okay, but this is a trickier question, I think. So it's actually a deliberately tricky question because this is something that I've seen a lot of people have a misconception about. So getting back to this formula, intuitively, intuitively, you would think that the nearby pixels are very positively correlated, right? And I hear people say that sort of thing around variational autoencoders all the time. But the truth is that conditional on the representation, these pixels are totally uncorrelated. There's no correlation between neighboring pixels, conditional on the representation. Why is that? Okay, I think this is worth actually writing. What is this? I'm going to clear this. Clear. Or you know what? I'm going to the second board. Here we go. Why is this uncorrelated? So we have that xi given zi is normal with some distribution. Mu theta of zi, and then sigma theta squared zi times the identity matrix. And okay, what is the dimensions of MNIST? So it's like 28 times 28, 784. Okay, so this is a 784 dimensional. So what this distribution means, so I'm imagining you have your 28 by 28 image. I turn it into a length 784 vector. And then the distribution that it's drawn from, this is drawn from some multivariate normal distribution. Here is mu theta of zi. So I'm gonna, actually I prefer the like block notation. So I have 784 of these mu's. So here's the first mean, the mean of the second pixel, the mean of the third pixel, and then the mean of the final pixel. Right? So that's the mean. And then I have a variance or covariance, right? Because it's a multivariate normal distribution. So the covariance of a multivariate normal is going to be some big square matrix. It's going to be 784 by 784. Its values give the correlation between neighboring pixels. But the point is that this is an identity matrix. So I'm multiplying, this is like a sigma along the diagonal and then identity matrix everywhere else. So what it looks like is like you have a sigma squared theta zi, you have the first one, so like theta comma 1, and then all the way down to sigma 784. And that's like some big diagonal elements, and then everything else is 0. Right? So most of this matrix is zeros. There's just this kind of diagonal terms which have real kind of actual values. So what this formula is telling you is that given zi, I have different variances on each pixel, but I have no correlation between the pixels. The no correlation is coming from the fact that the off-diagonal elements are all 0. Okay. So that's how you can think it's true. So the natural question then is like, why is it that when I generate an image, the pixels are correlated, right, between the neighbors? So the reason it actually does happen is because of the means, right? So for a given zi, your mean function, right, the first and the second means will typically be very close to one another, right? So if you have a very high pixel value for the first pixel, then the second pixel will often usually be high as well. But that is the thing that ties together the images at the end. It is not this variance matrix. Okay, so just I want to clear this up because I think it's important to understand these sort of technical points. Otherwise, it's too easy to just manipulate and run other people's codes without understanding what's going on. Okay, so I'm gonna now just build a little bit more of your intuition around this. Okay, so how does the decoder work? So remember, decoding is the process of going from the Z space out back into the image space. So think of it like this. I said it was some big multivariate normal distribution, right? And it's a 784 dimensional multivariate normal distribution. So that means that every single pixel is associated with kind of a univariate normal distribution, right? Every single pixel here is like, it has, yeah, it's kind of small, but you can kind of see here, there are these tiny little normal distributions, right? And what I'm trying to say is like, in the image, so, okay, I'm drawing kind of two samples given this particular zi. So imagine this is like xi drawn from one run, and then I draw xi again, and I get two different 4s, because this zi lives in the 4 region of the data space, of the latent space. How did I get those two different 4s? The point is that underlying these observations, there is some sort of distribution over the values of each pixel. These really narrow ones are saying that for a lot of pixels, given that you see this latent code, you can be pretty sure that a lot of these pixels are just 0, right? So they're all just spikes right at 0. So they never have any pixel value. But then some of the other pixels have positive values, or like they're a little bit wider variance and they're centered around something positive. So these are going to be the pixels that show up in darker gray. And the way I'm showing the shape of where those are coming up greater than 0, it's in the shape of this corner of the 4, right? So, you have around the corner of the 4, you can be pretty sure that you're going to see some sort of positive kind of darker colored pixels. And the way you see that idea of wider densities. So each one of these pixels correspond, well, the means, sorry, I don't know if you see this. Oops. So the means of each one of these pixels is that mu theta, or it's like the jth coordinate of that mu theta. And then the variances of each of these mini pixel normal distributions is given by the sigma squared theta z. Okay. So this is how the decoder works. You have a mean function, you have a variance function. This you have it applied to every single pixel, and then you just ignore the correlations off the diagonal. Okay. Yeah, so that was an example where I show like a 2-dimensional z. Usually you would have a larger dimensional z, right? Usually you want a latent code that's 60 to 100 or something like that, right? There are many different ways that your samples could be varying in the kind of underlying representation space. So you want to have enough dimensions for that. The original paper had d equals 20. So how does my picture apply when it's higher dimensions? Well, basically the same picture, you can still draw it, except instead of conditioning on a point in a 2D plot, I condition on its values across each coordinate of z. Okay, so here's another question. So I think we're on question 5 now. Question 5, what is the dimensionality of zi in this picture? Here's zi. Can I give it a minute? This is an easier question. Anyone? It's quiet. I know it's been an hour, but here's the question. I show you this picture. Here, z was 2-dimensional. Now this is my new representation of the z's. What is the dimensionality of z here? I'll give it a minute. Okay, we have one answer. And we have disagreement. Okay, this is it's not quite, but maybe this wasn't clear. I'm glad to clear it up now. So the dimensionality is actually 1, 2, 3, 4, 5, 6, 7, 8. Right. There are 8 numbers. So here there are a couple negative numbers, a couple positive numbers, but these 8 numbers summarize the essential content of the image. So I like using this as basically like a bar chart that summarizes each latent dimension. So the answer here is 8. Okay. So that is the decoder. So the decoder is how you go from the latent space. It could be, if it was 8-dimensional, usually it's gonna be like 20-dimensional to 100-dimensional, and then you generate an image. And different configurations of these z's. So like if I move this coordinate up to here and I draw this coordinate down to here, then it's gonna change the digit that comes out, right? So maybe it might change from a 4 to maybe like a slanted 4 to then like a 9, something like that, right? So we'll see an example of that in a minute. But first, I'm going to talk about the encoder. So the encoder is, you've observed some xi, you observe some new data point, and you want to get something like the posterior. You want to get a new, given a 4, you want to get something that, like, I think the representation should be about this. But the thing is, you cannot, this is such a general framework, right? We're looking at arbitrary mu's and arbitrary sigmas, that you do not have the posterior available in closed form. You can't just write down a formula and get the right answer. So what instead we'll do is we will approximate the posterior, right? So we'll say that this pz given xi is going to be about this q phi. Q phi, depending on different phi's, are each going to be a different distribution, right? So imagine in the variational picture, there's a whole bunch of q's. Each of the phi's corresponds to a different point in this space. So we need, the question is going to be, which of the phi's will bring us to this point? Okay. So let's see. This is going to be how we're going to approach the problem. We're going to say that q phi is going to be normal distribution. It's a normal distribution over the z space. And here, the mean of that normal distribution is given by this mu phi. This is like an encoding function. And you're going to have some uncertainty around where you put it. That uncertainty is going to come from the sigma squared. And for each of the images, you're going to have a different location in the representation space that it's centered around, and a different variance potentially as well. And I think this should have also an identity. This is a diagonal matrix with variance sigma squared phi. Okay, so some intuition. So you have some image. So here I see a 6. Before you have observed the 6, you have some distribution over where it might go in the z space. So here, the prior is a normal distribution. What did I write? Or no, yeah. I'm going to suppose that the prior is some sort of normal distribution centered around 0. And then once I observe the digit, then I'm going to move it to some new location. So it's just like in the beta binomial, where in the beginning you started with some sort of beta that's kind of flat. You're not sure what the probability was. But once you observe the coin flips, then you were able to put it at some location. You're able to say like, oh, okay, I'm pretty sure that the probability of coming up heads is 0.1. Same thing here. Same thing is you had an initial guess over where in the latent space it should go. Then you observed a data point. You observed the 6. And then you were able to say, okay, I think it should lie in this region of the encoding space. And I think its variances, so the kind of the shape of this ellipse, should be defined by sigma squared. So maybe different xi's are going to have different shapes of these ellipses. Okay, so here's an example of an encoder when you're working in 2 dimensions. Right? So my representation is only 2-dimensional. In general, you're going to have a higher dimensional thing. So here's an 8-dimensional encoder. So I start with this 3, and then I encode it into these kind of 8 numbers. And associated with each of these 8 numbers, I have a mean. Right? And I also have a variance for each dimension. Right? So the mean is coming from the mu's, and the variances of each coordinate is coming from the sigmas. Okay, this is how it looks like in code. So first, this is the encoder. This is the thing that takes a single image. So it starts off with image side, and it's 784, right? So this is MNIST image. It's encoding it to some 400 dimensional H, or sorry, this is not encoding. It's first doing some linear, it's actually just a 1-layer network. And then it's encoding it into some sort of Z-dimensional code. So I'm gonna summarize this code using this picture. Let me zoom out a little bit actually. Okay, so how does this work? What is encoding? What does it do? X here is some 784 dimensional thing. So maybe X started off as an image using kind of PyTorch notation. I say I'm going to unwrap it into a length 784 vector. That becomes your input. So the reason I've drawn everything as kind of either gray or orange is because the gray is the background, and then the 8 is the orange. And most of the pixels are going to be just gray, but then the pixels corresponding to the 8, these are the orange. These are used as input to some network. Now, what does the encoding function do? Well, first, it applies FC1 on X, and then it applies a ReLU on that. What does FC1 do? FC1 turns this image, which is 784 dimensions, into some H-dimensional thing, so some 400-dimensional thing. So it takes the 784, converts it to some 400-dimensional thing. That's what H is, 784 dimensions. Now, what happens after that? Then I apply FC2 to H. So what is FC2 going to do? It's going to take this H, and it's going to turn it into this mu phi. And here, mu phi is only 20-dimensional, right? So it goes from this 400-dimensional thing to just some 20-dimensional mu phi. That's what this element here is. This second element, this is the log variance. So, I mean, I'm just writing down the variance here, but it's actually the log variance. And this is another 20-dimensional thing. Okay, and in the end, you end up with this kind of each coordinate corresponds to its own normal distribution. It's normal distribution with some mean mu and some variance sigma squared. Now is the next question. Okay, so I drew a picture and I showed you some code, and I want you to relate the two together. So FC2 and FC3. So look at the code again. FC2, FC3, they also appear again here. Where, if I were drawing the links, so right now I've only drawn the variables, but if I'm drawing the actual network, right, where would the network edges go for FC2 and for FC3? So go ahead and write your answers in the doc. Let me try. Think of FC2 and FC3 as being like links between different layers. I give it 1 minute. So if you have even a guess, go ahead and list it now. I'll show the picture. So if you want to refer to the code and to the picture. I see a lot of people with the cursors there. And give it away in like 25 seconds. Oh, okay. We have some answers. I'll get it. So I'm going to move to slide 3 on the Jamboard. So the question again, we have this kind of whole network that I've drawn here. I'm asking what is FC2 and FC3? Where does it lie? So let's look on the Jamboard. So I'm going to first copy over the network. So right, we had some sort of input. We unwrapped this image, and there was like the pixels with the 8. And then the actual network, okay, first is the input layer. And then there's this H layer. And then there's a mu and a sigma squared. Mu, oops, mu phi. H, X. Okay, I just copied over the figure, right? So here's input H, and then those mu and sigma squared. And then the question was, okay, FC2, FC2 and FC3, where they go? And the answer is, okay, so FC2, let's do it in red. FC2 is linking H to mu phi. And it's actually a fully connected thing, so I should be writing it like a full network. How do I know that? I know that because when I look at the code, FC2 is a thing that turns H, which is this hidden layer in the network, to mu. This first output is mu. Okay, so that is FC2. And what is FC3? Okay, now it should be clear. FC3 is the thing that turns H into sigma squared. So it's going to be this guy. So draw here. So this is FC3. I'm going to draw H into the sigma squared phi. Right, so it's the same kind of fully connected network between H and the sigma squared. Okay, so that is answer to that question. Okay, so that is basically all I wanted to say about the conceptual, kind of like the theory. Here's an example of what it looks like if you try training the notebook. And I have actually created this animation in R, and you can see the animation in the GitHub repository, like the R markdown that defines this animation. The encodings that I got were in the Colab notebook. And what I'm showing you here is I'm moving along the latent code. So here is a 20-dimensional latent code. And as I change the latent code, I'm changing the observed data, right? So here I'm traversing the latent space and I'm noticing different observations. So this is just the mean. I'm not looking at samples. So it's just how does my mean function mu theta change as I go from one representation to the next. Okay, and yeah, again, if you want to try it out, the VAE example is in this GitHub repository. I just copied over. Most of it is just from some PyTorch. But in the end, it's actually, we already just saw this whole module, right? So it's doing this encoding, decoding, and then it just trains here. And that's it. Here, I'm collecting all the data to make that kind of fancy figure. But the whole of the training is just this. Okay. So that is the main point for variational autoencoder. I'm going to skip how it's actually optimized because we're running a little bit low on time and I want to get to the next topic. If you're curious about how VAE is actually trained, you should check out this notes and feel free to reach out if you have any kind of questions about it. But the idea is it's basically doing some sort of stochastic optimization to get the right choice of theta and the right choice of phi. But I think it's important to understand exactly how the model works, right? In terms of what are kind of the symbols that you should use to remember what everything in the model does. If you can remember that in the pictures, then I think figuring out the optimization isn't so bad. But first, just understanding the model actually takes quite a bit of effort. Okay, so we're going to skip ahead past the reparameterization trick, and we're going to talk about representational analysis. But I'm going to give everybody a 1-minute break before we go into the last half hour. So yeah, or maybe like 1.5 minutes. So just stretch, drink water. It's been hard, I know. Yeah, of course. The slides are actually in the GitHub repository as well. So if you go here. Actually, the R markdown I used to create the slides are also here. Yeah, it's using GGN. Actually, you can check out the code for the GG animation. I think it's one of these. Yeah. This is doing all the GG animate. And all the data used I saved all the data too, so you can just run this on Markdown and you can get it. Data is just here. Okay, so let's get into representation analysis. This is a much shorter section. I mainly want you to be aware of this topic. And we will be able to see a little bit of some classical statistics that I think a lot of people don't know that much about, but I think is very powerful. Okay, so what is the whole point of representation analysis? This much. Okay. I think a lot of science emerges by having useful tools for introspection, right? It's easy enough to just write a new model, right? But the more information you can gain about what its properties are, the better off you'll be, right? Science proceeds by gathering new observations, right? Usually in most sciences, you gather new observations about the natural world. Right? You build a new kind of sensor, you explore a new part of the planet, and you observe something that other people have never observed before. Machine learning is a kind of a funny type of science where the things that we observe are the models that we create. Right? Typically, what most people do is they just observe the test performance, right? And that is a very natural way to gather information about a model. If it does really well on a test set, that is useful information. But there's a lot of other kinds of observations you could gather about your model, which would help you advance your scientific understanding of things, and which I think is not as common as it ought to be, right? If you had a way of collecting new observations about the model itself rather than just its test error, then you might be able to debug models that don't really work, and you might understand what specifically was it about this model that let it do so well? And maybe you can carry over that idea across many different new situations. Okay. And kind of a last point is like, I think, sometimes people talk about science as if it's like science is only the complicated things, and research is like, we only pay attention to the things that are, far too complicated for most people, right? But that is, I think, the wrong attitude. I think a real scientist is able to look at something very simple and something that most people think is just like an everyday, ordinary thing, and they're able to look at it in a new way, and they're able to gather kind of new observations and new insights about something that might otherwise seem very ordinary, right? And I think that's kind of the thing I like about this whole representation analysis area, is that you can take what might otherwise seem like a very mundane model. You can take a convolutional net with Batch norm. You take like a standard U-net, and then you can learn a lot of things about it that most people don't even know just by analyzing the representations better. Okay, so let's think. What is representational analysis about? So deep learning models learn distributed representations of data. This is kind of one of the fundamental principles. It's like each neuron reflects some kind of distributed, or each neuron has different kinds of aspects of the object that you're observing. And that object that you're observing, you end up distributing information about it across all these different neurons, right? Now, that's how these things are motivated, that's how they work. But there's a whole bunch of questions you can ask about exactly how are these representations operating, right? So you might ask, how quickly are different layers learned? Maybe one layer is learned faster than another. You might ask, how do representations compare across models, right? So I might learn a model with 20-dimensional latent code. I might learn a model with 100-dimensional latent code. And you might want to know, okay, are these similar? In what ways are they different, right? Kind of effective dimensionality is the same kind of question, right? Like maybe I gave it 100 dimensions to work with, but it only used 20 of them effectively. So that's a thing that you might be curious and it's not obvious right away. And finally, like, there are all these different kinds of heuristics that are used in deep learning, right? So you might use transfer learning, you might do batch norm, you might use different kinds of optimizers. How do those actually affect the training or the resulting model, right? These are questions that you cannot answer just by looking at the test errors. So we're going to instead use some tools from representation analysis. The main idea I'm going to talk about is something called singular vector CCA, SVCCA. I'm going to talk about it using a simple, fully connected network. Nothing fancy. I can discuss a little bit how it operates in convolutional networks. It's pretty similar, but then I mainly want you to understand how does it work for a fully connected network. And in the process, I'm going to be able to talk a little bit about canonical correlation analysis, which is maybe one of my top 3 or 4, maybe my top 3 statistical algorithms. Like there's like linear regression, Benjamin-Hopper procedure, and canonical correlation. Okay. So here's the example that we're going to be working throughout. Again, this is all in the GitHub if you want to rerun everything. I've made up these 5 functions. This is a kind of blue through green. It's a one-dimensional input. Okay? So x is between 0 and 1. The response is usually between -4 and 2. Nice. This one goes down pretty low. So it's a 5-dimensional output because you have these 5 different curves. Each of them has one-dimensional input. I can learn a deep learning model for this, right? What is a natural deep learning model for this? You have 1D input, x, so here's just a square, 1D input. 5D output, y, here are 5 numbers in some rectangle. And I'm going to put 4 fully connected linear ReLU layers. So it's just like the stuff that we were seeing in the code chunks before. It is fully connected followed by ReLU, and I've stacked 4 of them. There are 200 neurons in each layer. So I'm just putting all 4 of these layers in this one big purple block. Okay, so this is what training looks like. I put the Colab notebook for it. Okay, so this is after it finishes. Let's wait for it to loop. Okay, come on. Okay, so it started off, it's trying to fit the thing. No, some of the peaks are not quite there yet. Okay, and then finally it brings down all the way down and it's pretty much converged. Okay, that is what it looks like to train a 5-dimensional output neural network on 1D input. Right? This is, I just saved it at, I think, every 5 epochs, something like that. Okay. So what were the representations that were learned? Right? This is a 4-layer network. We should be able to say something about this, right? There are only 200 neurons each. So here I'm showing the activations across all the samples. Right? So I have examples from 0 through 1. Or actually here I've evaluated it on new points between 0 and 1. At point 0, I can calculate the activations of each neuron for the data point at x equals 0. This is layer 4. Right, so layer 4, there are going to be some neurons which are negative activations. So here the activation is -15. Some of them are negative, some of them are positive at 0. But the way you read this kind of plot is each point in the plot, each color, each pixel is one value of x and one neuron. And I've kind of sorted the neurons so that neurons with very similar activation patterns are placed next to one another. So right, like all of these kind of neurons, the thing they have in common is they are activating, they have negative activations. These neurons all have negative activations at low values of x. These neurons all have high activations at high values of x. Here are neurons with positive activations. Okay, so that was the 4th layer. This is the 2nd layer. So even at convergence, notice the 2nd layer, this is less extreme values, right? So it's a lot paler color because you rarely have anything from -15 to 10. Most of the values are probably, I'm guessing this is like -2 to 4, minus 2 to 4 maybe would be realistic. Okay, but this is what the second layer looks like. Okay, here's the fourth layer again. So it's this layer, but then before it has fully converged, right? So, you know, I've been saving these activations from the very start to when it has fully converged, right? So, you know, I can, let's wait for it again. So it's converged. Okay, imagine I saved it now, right? I saved it like 40 epochs in. And then when I save it at that point, that's what layer 4 activations look like. So the main thing that's different, they're kind of not as dark in color. Right? So here they're kind of a little bit more strongly activating, versus here they're a little bit more weakly activating. Okay, so I think I have some questions on this. Okay, I basically have already explained that. Okay, maybe let's do question 9. What are the dimensions of the matrices that I've plotted in these heat maps? Someone want to give it a shot. Actually, I think you can only say the number of rows. How many rows does my matrix have? I didn't tell you enough information to be able to figure out the number of columns. Anyone? We're running out of time, so I can't give you very long. Okay, people are tired, but I'll give you an answer. So the number of rows is 200. The way you can know that is because this network had 200 neurons. And so there are 200 neurons, and each row of this matrix is a different neuron. I'm just plotting each of the neurons as a separate row. The reason you don't know the number of columns is because I've evaluated them on a small grid, and I haven't told you how fine that grid is. And to be honest, I forgot how fine of a grid I evaluated this network on. So however many that is, that'll be it. Okay, so this is all kind of nice pictures, but then, you know, to be real scientists, you need to quantify things. So there's an intuition somehow that layer 4 after 50 epochs looks pretty similar to layer 4 at the end of training, but layers 2 and 4 look quite different from one another. So can we quantify that? Can we give a number that assigns how similar these matrices look to one another? Okay, so basically, I have these two matrices. I have n samples, you can think of it here as like n neurons. And then I have D1 features or D2 features. So I have the number of samples that I'm evaluating it at, and I have the number of neurons that I have, right? So I'm just abstracting away these pictures, these kind of activation matrices into X and Y. You want to compare these two activation matrices. Now, if they were vectors, this would be a really easy question, right? If D1 and D2 were both 1, so 2 long columns, then asking how similar they are is very easy. You can just calculate whenever you have 2 vectors, you can calculate their correlation. But when you have many columns like this, it becomes a much more complicated question, right? Like, what is the correlation between a pair of matrices? That's not an obvious question. I think this is in 1934, 1930. He has an example with like basically like a whole bunch of commodities, their prices, and a whole bunch of commodities, their yield. And these end up being two big matrices. And he wanted to understand what's the relationship between like price and demand, price and supply. So he needed to have some sort of correlation between matrices. And that's this whole paper. How does it work? So some mechanics, this is not obvious, but I think it's a really beautiful geometrical picture. So first is you can view a matrix as d vectors in n-dimensional space. This is different from how we usually think of plotting a matrix. Usually when I show you a matrix X and I ask you to plot it, what most people would do is they would make column 1 one dimension of the plot and column 2 another dimension of the plot, and they would plot all the data points along those two features, right? I'm asking you to do the opposite. I'm saying you have an n-dimensional space now. So you view that dimension of the space as the number of rows of this matrix. And each one of the columns gets some vector in that space. So this is a flipped way of plotting a matrix. So question, I won't wait for it on the doc, but if you want to write it on the doc, you can show it to people later and say that you knew the answer. What is the dimension of the matrices that I'm plotting in this diagram? So here I'm plotting two different matrices. There's matrix X, there's matrix Y. Each of these vectors are columns of these matrices. So here I have 2 columns. How many rows do I have? Right. So give it a second to think about it. So basically you have these two different matrices X and Y. I'm plotting the features as vectors in some ambient dimensional space. What is the original dimension of that matrix? Okay, so if you give it some thought, you can realize that this is going to be 3 samples, right? The reason you know it's 3 samples is because there's 3 dimensions. So each dimension corresponds to a different row of this matrix, and each vector corresponds to a different column. So these are going to be, here we have two different 3x2 matrices. Okay. These are very small matrices, right? 3x2 matrix is really tiny. But then you can make the same kind of figure abstractly in very high dimensions. So if you had 1,000 samples and you had 10 vectors or 10 columns for like 100 or 1,000 by 10 matrix. 1,000 by 10 matrix would look like 10 vectors. So you'd have 10 of these arrows in a 1,000 dimensional space. And it's hard to draw a 1,000 dimensional space, but that's why I'm just showing some simple example here. Okay. Now, okay, how similar are the matrices now? So I have this new way of plotting a matrix, right? I'm plotting them as each column is one of these vectors. Now the idea, the kind of essential idea, yeah, I know it's 3 samples because it's in 3D. Okay, yeah, this seems to be a common point of confusion. Let me start again. Yeah, so the idea is you view a matrix as d vectors in n-dimensional space. So, you have d features in n dimensions. So you have d columns in n rows. So if I'm viewing the matrix as d vectors in n-dimensional space, and I've shown you here x is 2 vectors in 3-dimensional space. So that means d is 2 and n is 3. So that's why it's an n by d matrix. So it's a 3x2 matrix. Does that make more sense? Yeah, it's just because of the dimension and the number of vectors. And here the dimension is this n. Okay, cool. yeah, that I realize it's not the usual way of plotting a matrix, right? So why is it a little bit counterintuitive? But once you have that representation, now you can imagine drawing the subspace that's induced by these vectors, right? So if I have 2 vectors in 3 dimensions, then I can draw a plane that's all the linear combinations that arise by combining these 2 vectors. Right? So you just think of like you have the 2 vectors, and then you think about the whole plane that's aligned to those 2 vectors. And the same thing I can do for the other data set. This is some other 3 by 2 matrix, and it's spanned by these other 2 columns. So it induces a different plane. Okay, now here's the key question. How do you measure the similarity of these subspaces? The intuition, and it turns out like the mathematics as well, is that the more aligned these 2 planes are to one another, the more similar you should call the subspaces, right? Versus if they were like kind of at angles, like very big angles to one another, then you think these subspaces are totally unrelated, right? So somehow the alignment of these planes is a good way to measure the similarity between these 2 matrices. Okay. So now I'm just trying to show you how do you think about these angles, right? I'm just drawing kind of 2 rings that are lying on the plane, and I'm showing you what is the smallest angle between these 2 rings, right? So they're like interlacing rings, you think about it, right? So interlacing rings, and you try to figure out what is points on these rings that are very closely aligned to one another. And that will be your way of measuring the kind of principal angle between these 2 subspaces. And that is exactly what canonical correlation analysis does. So here's the optimization problem. Optimization is basically saying this notation is, these are all the vectors in the first plane, here are all the vectors in the second plane. I'm trying to minimize the angle between a vector in the first plane and a vector in the second plane, subject to some constraint on the length. Right? If I'm allowed to make the vectors really, really close, like really small, then I can get the angle kind of arbitrary, right? But if I force them to lie along these rings, then I cannot make them just perfectly overlap. So under the constraint that they can't perfectly overlap, what is the most similar that you can make these 2 angles? And that is what the canonical correlation analysis problem solves. Okay, we're almost done. So that is how you can measure the similarity between these 2 subspaces. Some further intuition, when might you expect the 2 subspaces to be very closely aligned? You generally will expect them to be closely aligned if they share the same kind of latent information, right? So if one of these is kind of the number of, like the price of different commodities, and the other one is the amount of production for the different commodities, they might both be reflecting a few underlying factors. So they might both be reflecting the weather, kind of the amount of different kind of fertility of the seeds, right? So there are like a few different kind of underlying factors that influence everything across both of these matrices, right? Or another example could be like, here are your grades in physics class, and here are your grades in the math class. And then the latent variable is just like, how much time have you spent doing algebra, right? So yeah, the idea, when they share latent dimensions, then you tend to have very close alignment between the 2 subspaces. Okay, so this is how we're going to compare our activation matrices, but we need one more trick. The issue is CCA is a very computationally intensive procedure, right? It requires a matrix inverse if you want to solve the optimization, and doing a matrix inverse in deep learning world is really hard to do because deep learning world, we're usually operating on very large matrices. So what the idea is, you first reduce the dimensionality of these tables. So I turn the original X, I use the singular value decomposition, and then I extract just K of those features. So I'm turning X into a much narrower X hat. And now that I have X hat, I can do CCA on the reduced X hat and Y hat. Okay, it's just some intuition about the SVD, in case you haven't seen it before. It's a way of taking a high dimensional set of points into a lower dimensional set of points. So if you want to go from 2 dimensions to 1 dimension, what it would do is it would take these gray points. So all these gray points live in 2D, and then transform it to these orange points, which are points in 1 dimension. The way I transform it is I try to find the line that approximates the cloud well, and then I project it onto the line. So, and then the new representation says, where do you lie along this line? So I've taken 2 dimensions to 1 dimension. In general, you can take d dimensions into k dimensions. Okay, this is how it works. First, extract all the activations for your network, right? That's like these plots from above. I was just extracting all the activations from the network. I put them into this big matrix. Second, use the SVD to compute reductions. And so now I've taken these wide matrices and I've shrunk them down into far fewer columns. Now that they're much smaller, they're going to be computationally tractable. You can run canonical correlation between these 2 projected matrices. And this gives you a measure of the similarity between the 2 subspaces, right? I showed you that kind of principal angle. So there's the angle between the top 2 dimensions. In this picture, that's going to be all you're going to be able to do. But in higher dimensions, you're going to have several angles. You're going to have a kind of a top principal angle, you're going to have a second principal angle, and it's kind of a sequence of angles that summarizes the similarity between your 2 high dimensional subspaces. Okay, and so now you can use that to compare things, right? So here I have layer 2 subspace, 50 epochs in, and I think it's like 1,000 or 1,200 epochs in. So it's many epochs change. Yep. And then the similarity, it's almost 1 across all of these 8 angles. So I've computed 8 of these subspace angles, and they're all very, very similar. So the way you read this is that the network, 50 epochs in and 1,200 epochs in, at least at layer 2, there's not that much difference. The activations are very, very similar. So I've given a quantitative description of this thing that visually also seemed kind of clear. Versus layer 4. Layer 4, this is layer 4, 50 epochs in, and here's layer 4 at convergence. If I look at the similarity plot, now, okay, there are a few angles which are still pretty similar, but there are now more angles that are less similar, right? And the average similarity is this red line, right? So kind of you now have a quantitative description of saying like, okay, layer 2 converged after only 50 epochs, but layer 4 took pretty much all the time for training, or it definitely did not converge after 50 epochs. Okay, you can do other questions. You can ask, how different are layer 2 and layer 4? Same sort of calculation. I extract the activation matrices, I run SVCCA, I get each of these principal angles, and I can see, okay, it's not as similar as epoch 2 across epochs. Sorry, it's layer 2 across epochs. Okay, here's a picture from a paper that's using representation analysis to understand transfer learning. So it's able to tell you, okay, these are basically like the similarities between the activation matrices. And it's able to tell you that, okay, when you use a pre-trained network, that increases the similarities between the kind of initialization and the end of training. Right? So there are all sorts of new tricks that you can come up with once you realize which layers are more and less similar. So here you can see the gap is also changing. So here there's not much difference between the pre-trained and the random initialization. So the very late layers, it doesn't really matter whether you pre-train or not. Versus the very early layers, it can make a big difference if you pre-train. So that gives you some ideas about how you should transfer. Maybe you should only transfer the first few layers and you don't have to worry about transferring the rest. Okay, we are done. Just very quick overview. We talked about variational autoencoder. Starting from the very beginning, we saw the beta binomial model. So it's like the very first Bayesian example. we did a lot of pictures. We played around with some interactives. We looked at MNIST. There's a Colab notebook, which just trains the thing on MNIST. We looked a little bit at singular vector canonical correlation. So we first looked at the pictures. And once we saw the pictures, we thought, okay, there ought to be some sort of theory for how to summarize these pictures. And that's where we went back to canonical correlation and went into that discussion about how do you find the angle between subspaces. There could have been many other topics I brought up, right? We don't have time to talk about GANs and hypothesis testing or predictive inference or empirical Bayes, but these are all interesting areas, and I put links to good papers that have that link between machine learning and statistics. Here are some great essays on the similarities between statistics and deep learning. And the last point I want you to leave with is, I know this session was titled Statistics and Deep Learning, and people like to draw distinctions between things a lot, but I hope this session helps you realize that there are connections between them that are more subtle than might be obvious at first, right? We can go from statistics to ML and go from ML to statistics, and you learn things either way. Okay, that is the talk. Feel free to reach out. I hope you enjoy the rest of the sessions today. If you have questions, I don't know if there's like a way that we can have a second link, we can continue discussion, or yeah, instead of some time to talk a second. Yeah. Yeah, thank you, everyone. I appreciate it. I hope you enjoy all the sessions. It sounds like a really neat event.
Hello, Kris. That went well. So I think we have some questions in the chat window like we usually have them. I saw one now. Do you have access to the chat window, Kris? Before the thank you messages. Yeah, let's see.
Yeah, so a question about the link to the material. So all the material is in this GitHub repository, actually.
Okay, so everyone, again, like we shared on the first day of the bootcamp, we shared it yesterday, we shared it today. All the links to all the sessions in this bootcamp, as long as you're registered, will be shared with everyone. You have access to the videos, you have access to the learning content. So Kris, that was a long class. Thank you.
I hope people learn some interesting things, or at least like the links to learn more.
Yeah, we hope that next year it will be in person. It's usually fun, the classes that we've had in person. It's usually such a great experience, but we're trying to make do with what we have online.
Yeah, no, I hope everyone, it's a weird time in the world right now. I hope everyone is staying healthy, safe. Okay,
someone has a question in the chat window, Kris, just after your GitHub link.
Oh no,
from Emmanuel.
You leave it as the hats. So you take X and Y, you convert them to the reduced X hat, Y hat. So you might go from, you know, like 1,000 neuron dimensions to like 50 CCA dimensions. And then you stay with those 50 dimensions, and then you can do canonical correlation between these two 50-dimensional matrices. Does that answer what you're thinking?
Emmanuel, if you're online, kindly respond in the chat window. Kris wants to know if you get that well.
Yeah, we're happy to explain.
Okay. Okay, that's not Emmanuel, someone else.
Okay.
Okay, it says it gets that. Kris, yes, if you don't have any other thing to share for now, I would like to announce that everybody can go back to the main event. And we can bring this session to a close.
Sounds good. I hope all the organizing is going well.
Yeah, it is.
Virtual conference always hard.
Oh, well, we're trying to make it work with the internet. Yeah, there's a class going on right now on Big ML. So everybody will just meet in the main room again. Okay, thank you everyone for joining. Kris, everyone says thank you in the chat window. You have many thank you. A note. We are happy to have you. We were in this class yesterday, and now we are here again. Okay, so team, kindly click on leave room, and then you can leave the breakout room to join the main session. Our next session is by 3 p.m. Our next session, the full session is by 3 p.m. It's by 3 p.m. It's mostly about career questions, asking from real people. So please come with your questions, and we're good to go. So you can leave the breakout room, take some water, rest a bit, and let's meet again at 3. Bootcamps are usually intense. I know we've been at this all day.
Yep, take care, everyone. See you all.
Okay.